23, lab number 8, the photoelectric effect. For this lab, for part A, we want to make sure that you understand what's going on when the photoelectric effect happens. This is going to be our, down here is our box. This is our apparatus for the photoelectric effect. It's kind of hard to tell what's going on inside there, and so what we can do is we're going to go ahead and try to model it by drawing some diagrams, and you can replicate these or add to them in your lab report that you're going to end up turning in. There is also a link to a PhET simulation, which shows kind of basically what's happening inside one of these photoelectric effect boxes, and you can go ahead and play with that if it helps you as well. So let's begin by kind of looking at what happens when you have atoms. This is simplified, but what happens if you have atoms with electrons orbiting them, okay? These electrons are attracted to the atoms, and so it takes energy. If you wanted to remove this far from the atom, it's going to take some energy. We define this energy as the work function of this material. It's different based on different materials and how strong these forces of attraction are. And so this work function is the goal of the lab. This is primarily what we're interested in experimentally determining for an unknown material. And so with that being said, it would help to start out by thinking of what happens if a photon comes in and hits that electron. Okay, photons are quantized in their energy levels, and there's a formula for finding energy based on the frequency. Okay, it's really simple. You should already know it or be able to easily look it up. Rudolph's Planck's constant. But you can find the energy of this photon, and it hits this electron. Now, this energy hardly ever, it'd be a very big coincidence if this energy happened to equal exactly the energy to take it out. Usually this energy would actually be more than the energy to take it out, in which case this particle is going to have some velocity, okay? And that's going to be represented in kinetic energy, which we denote with a K, if you remember from Physics 121. And so this particle that gets knocked off by the energy of the photon, okay, is going to have kinetic energy equal to that energy, because by conservation of energy, all of it is going to be transferred into it. So it's going to equal this energy, this K is going to equal that energy minus this work function, okay? And so that's the key formula, which you should find in your student packet as well for the photoelectric effect, is what that formula relating these things are. So now the trick is, how do we measure this kinetic energy? And so we can do that by measuring current, okay? And so what we have here is, let's pretend that this is our sample that we're interested in, and these are photons. Now these will knock off electrons. Some are going to be traveling faster than others based on how close to the atom they are. In this case, we're only going to be looking at the outer ones, because that's what the work function is based on, just the outer electrons that have the highest kinetic energy, which is why we usually denote it K max. Because these lower ones may get knocked out as well, but they're not going to have as high kinetic energy. And so these electrons come out, and we'll have a collector plate here, and we'll have them go through a wire down to ground. So basically, they're just attracted here, and they're going to go through, but they're not going to change their kinetic energy. And so this, based on how fast they're moving through here, which we can define as the current, okay, the electrical current, as these electrons move through this wire, based on how fast they're going, it's going to be proportional to the current. And so this K max is going to be proportional to the current. And what we're really interested in is what happens, exactly what this K max is. Because each electron may have a different, and there's going to be more electrons or less electrons that'll affect the current. Depending on the intensity of the light, this current is going to vary. But what we can do is we can kind of apply a trick. And what we're going to do is take a plate here, and we're going to connect it to a battery, okay? And so this is how we draw batteries usually. And this battery is going to charge this up to a high voltage, okay? And you don't need to know too much about voltage. Probably some of you are aware of, are familiar with voltage, but those who aren't, it's okay. Basically, what a voltage does is it applies a voltage difference from this plate down to this plate. We'll call this V2 or V1. This voltage difference indicates an electric field, which is a force, okay? And so any electrons that come out here, they're going to start moving this way, but they're experiencing a force that's going this way, okay? And this force causes them to slow down. And so as we increase the voltage of this battery, as the electrons come through, this current's going to decrease, okay? And there's going to be a point where this current goes to 0. And when that happens, these high energy photons, the highest energy electrons highest energy electrons come out here and they stop right before the plate and they're pulled back, okay? And you can see that in the FET pretty easily. And so what we can do is model based on the voltage difference here, which we're measuring, and we just define as V. We'll just define the difference as V. This voltage difference times the charge of the electron, that's the work being done on it, and that's how much the energy is taken away. And so we know that right when this current goes to 0, the voltage difference required to get this to go to 0 is called the cutoff voltage. I guess I can label that there, cutoff. The cutoff voltage, and this cutoff voltage, if we times it by the charge of the molecule, or the atom, well I guess in this case electron, the charge of the electron, which is E, you can look that up, is going to equal this kinetic energy. So that kinetic energy that we're interested in here, because it gives us, it's the key to finding that. This kinetic energy is going to be related like this to that cutoff voltage. And so if we can measure this, we can find that, and once we know that, if we plot frequency and this, you should have in this section derived a linear formula between them. So linear is just the slope of a line, right? Y equals mx plus b. In this case, y would be k max, and x would be the frequency. Okay, and so we can plot this and find the slope and this b based on plotting our data. Okay, and we're going to do that in Excel in the next part. And the key thing is, what does this m and b mean in regards to the work function or Planck's constant? Okay. So that's the explanation here. Again, you just need to kind of replicate maybe some of these diagrams. In all actuality, this is a little bit more complex. This battery, actually, we need to connect it like this. That's not too important for our purposes here. But yeah, just replicate this a little bit and write in some sentences and derive the key formulas. I think that's one. This would be another one. And then a formula relating phi to F, a linear formula with phi in it would be the other two. So those three formulas, and kind of explain how they interact and kind of what I went through. Feel free to play around with the FET. One thing that you'll note in the FET is that it measures you need to go backwards for this voltage, this V, is actually negative in the FET. And that's just how it's just the notation they use. It doesn't actually matter that much. So you'll need a negative voltage when we're just defining it as positive here. All right, so this is the experiment, or the apparatus that we're going to use for this experiment. So it's basically the same thing that I just drew on the board. What we're going to do is we have a photocell where we're going to put in light. And I have these different LEDs. They have the same, they're called coherent light sources, so they have the same wavelength. And what we can do is put these in where this photocell is, and then it'll register the current that is generated, as well as the voltage being applied. So what we can do to start out with is go ahead and just set this down to 0. And I'm going to go ahead and turn off the lights here, or dim them a little bit, just to protect the photocell. I'm going to plug this in. We're putting that light into the apparatus, and we're generating a current of 1.14 nanoamps. Okay, now this is negative. We don't need to worry about that. It just depends on how you orient the sensor, and so you can just take look at the absolute magnitude is what we really care about. But when we're at about 0 volts, this is the current that's flowing just naturally as the electrons come out, are knocked out by the light. So what we can do here is just increase the voltage. We can see this go down, right, or closer to 0. We see it getting closer and closer to 0. And the point where it stops is our cutoff voltage that we're interested in. And so there's a coarse adjustment knob that I'm doing right now. Then when I get close, oh, well, that was lucky. Okay, I went a little bit further. when I make these small changes, I use the fine adjustment knob, which just varies the voltage even slighter. And once we're within about maybe 0.2, probably close enough. Okay, there we go. So current's about 0. So this is our cutoff voltage. Like I said, 5 point, kind of fluctuating, say 9.97. Let's call it 9.7. And that's about our current there. And so what we can do is I'll just cover this. The wavelength of this light is 472 nanometers. And so you're gonna wanna record 472 nanometers and then that cutoff voltage in an Excel sheet. And we're gonna go ahead and do this for 4 of these different LEDs. Oops, putting it in the wrong place. So here's the next one, it's 505 nanometers. Okay, so let's go ahead and turn this down. Okay, there we go. So we'll do kind of the same process. Try to get it up to 0. Okay, there we go. 0 amps and 0.475 for our cutoff voltage. So let's go ahead and move on to the next one. Okay, 588 nanometers. Okay, this one's actually pretty close. So we'll just turn it down a little bit to get back down to 0. Oh, maybe it wasn't as close as I thought. Okay. Here we go. 0.146 volts for 588 nanometer light. And then our last one here. And again, I'm just covering this to protect it from the ambient room light. So it's 525 nanometers. You can see. And we'll go ahead and turn up the voltage. Watch the current decrease. Okay, right there. Okay, 0.424 volts. And that's gonna be everything here. I'm gonna go ahead and put the photocell back on, photocell cover back on. That should be all the data you need. Again, you'll have to convert from your wavelengths into frequencies, and then you're gonna have to convert from these voltages into the kinetic energies, and then we'll use that linear relationship, the standard photoelectric equation. In Excel, what you'll do is you'll plot as the x value, right? You're going to plot as the x value the frequency, and then the y value will be that kinetic energy. And then based on the model that we just developed, you should be able to fit a line to it and then find what the intercept is, the y-intercept to be, and that's going to be the work function. And then the slope would be Planck's constant. So good luck with those calculations, and thanks for watching.